and welcome! Today I would like to take care of this 486 mainboard which I got in an awesome donation from one of the viewers some time ago. This board is manufactured by the company Soyo. It already has PCI slots and is one of the later 486 mainboards. First, let's take a closer look at obvious damages. First of all, one of the memory slots is broken on one end. Nearby there is a footprint where a voltage regulator used to be. It has obviously been ripped off. There is still one of the pins sticking out of the board. This regulator is needed to power 3V CPUs, and 5V CPUs would work also without it. Here was the battery. Likely it was removed not too late, so the bigger damage could be avoided. Still, as you see, some electrolyte already started to leak from the old battery and corroded the contacts. There are some hot glue leftovers which have kept the battery in place. That can be removed with some alcohol. And against the oxidation, I will use some white vinegar to clean it. Looks like someone who removed the battery did it with a pair of pliers and scratched the PCB a bit. But there are no traces, so that's fine. As far as I know, this board came from a scrapyard, and just as so often, the pins are bent. Let's now check for shorts. Looks good, there are no shorts on the main power rails. But also here one pin is bent. On the back there is still an old sticker, Targa 486DX280. Targa was a German company which sold PCs and electronic office equipment in the 90s, so this board was obviously sold with an 486DX280 CPU from AMD, since Intel didn't have 80MHz 486 CPUs. There are some small scratches on the PCB. Let's check for continuity. Looks good as well. Okay, let's try to bring it back to life. First I will need a BIOS ROM. That one can be obtained from the RetroWeb. The manufacturer is Soyo. It is a socket 3 board and it has 3 PCI slots. Here you go, it is Soyo SY-030H, or more to be precise, it is SY-030H, which is the same but with a 0 insertion for sockets, as it is stated in the notes. The latest BIOS version is B2 and is from 7th December 1995. Let's take that. I used my T48 programmer and wrote the BIOS image onto an EEPROM off camera. Now we have to set some jumpers. Some of the jumper settings are documented on the PCB, but by far not all of them. Just frontside bars and cache settings seem to be mentioned. The frontside bars seem to be set to 40 MHz, which would confirm once again that the previously used CPU in this board was indeed a DX280. But there are some more CPU related jumpers to set here. So thanks to the RetroWeb project, once again, I could set all the jumpers as I need those. The CPU which I'm going to use is an Intel 486DX266, a 5V version which doesn't require the voltage regulator. So the voltage jumpers are now set to 5V. Previously they were set to 3.45V and the frontside bus is set down to 33 MHz. Now let's check that the CPU gets its voltage and the clock. For that I use a piece of wire inserted directly into the socket. Clock is pin C3, ground and voltage are distributed over multiple pins. Ground can be found, for example, on pin B3 and voltage on C4. The yellow cable is now inserted into the clock pin. Let's see. Nice, here we have 33 MHz as expected. The voltage is also 5V as it should be. Time to insert the CPU, the post analyzer and of course the PC speaker. And we do have some postcodes as well as beeps, which signal the missing memory. No problem, let's give it a memory module. The first memory slot is broken on one side, but it should still hold the module in place. For testing, it should be fine. This is a 486 mainboard which has 32-bit memory bus, so unlike in Pentium mainboards, which use 64-bit memory interface and require two 32-bit modules obviously, here one module is sufficient. However, most 486 mainboards don't work with the usual EDO memory modules and need FPM modules. So now the board complains about the missing graphics card. Once again, let's add a PCI graphics adapter. Let's also add a compact flash to IDE adapter in case the system will be ready to boot into DOS. And we have an image. Let's set the compact flash card geometry in the BIOS and see if the board can boot from it. Welcome to Microsoft DOS 6.22. Sysinfo detected a 486DX66. That's right. And the benchmark is terribly slow. Slower than a 33 MHz 486. Doesn't matter now, the board is booting. Let's continue first with the repair. So the rests of the old battery and the voltage regulator are removed. I also desoldered the broken memory slot. In my spare parts I found two 72-pin slots. I desoldered those ones from a donor board and they don't look quite the same. Unfortunately, I don't have slots at hand which would look identically, but technically that doesn't matter. I also freed the holes of the voltage regulator. This board supports two types of regulators with 3 and 4 pins. It's not clear which regulator has been used in the Soyo board from the photo on the RetroWeb. I know which ICs are usually used in such cases, but it's better to confirm it once again. Luckily, this board has been made by different manufacturers and there are some detailed pictures available on the RetroWeb project. For example, this 8-bit board is very similar and it uses the LX8385 regulator, which is specified for about 3 amps. In my scrap I found this pin-compatible LX8383A regulator. This one is even specified for over 7 amps, which is even better in our case, since I hope that it will remain cooler and will not need an additional heatsink. At least LX8385 would definitely need one, and as we can see on the picture of the 8-bit board once again, it has a small heatsink indeed. Well, let's see if we need it too. When soldering the memory slots, pay attention to the holes in the PCB. The memory slot has two plastic standoffs. One is thicker than the other, and there is only one way how you can place this slot. Also, when soldering such slots, especially used ones, I recommend to insert the memory module before you solder the pins. This will help to keep the pins in place, otherwise through the soldering heat they can be pushed up slightly and later you will not be able to insert the modules anymore. That is very annoying and hard to fix afterwards. So help yourself and solder the slots with memory modules inserted. And also don't solder all the pins at once. Do only 1 or 2 pins on each end first and then double check that the slot is upright. If everything looks good, do the other pins. So let's check the soldering work on the memory slots. All the jumpers are unchanged, so the CPU voltage should be at 5 volts as before, and the voltage regulator remains unused for now. Yay, the system posts and I can see an image on the display. That means that the memory slot is working properly. Now it's time to take care of the regulator. Now the jumpers are set in the way that the regulator is not powering the CPU. It should generate some voltage, but the CPU is still hanging on 5 volts directly, so the voltage on the regulator can be safely measured. The regulator can be set either to 3.45 volts, 3.6 volts or 4 volts. Let's set it first to 3.45 volts. Okay, we are getting nearly 2 volts. That is not right. Let's see what will be generated if the jumper is set to 3.6 volts. It's even less, 1.93 volts. Okay, now 4 volt setting. That gives us around 1.85 volts. Okay, let's take a look how this works. Here we have 4 resistors, 3 of which are connected in parallel and 1 is in series. This makes a voltage divider which is used to adjust the regulator. Let's take a look at the datasheet of the LX8383A voltage regulator. This is a typical circuit for this IC, and as you see there are 2 resistors on the output which divide the voltage and are connected to the adjustment pin of the regulator. The so-called reference voltage expected on the adjustment pin is 1.25 volts, and by selecting proper resistors, the output of the regulator can be adjusted accordingly. As shown in this example, if we take 121 ohm and 205 ohm resistors, the output voltage will be around 3.3 volts. This is the formula which have to be used to calculate the required resistors. Vref is the specified 1.25 volts for this regulator, and as you see the output voltage depends only on the selected resistors. So let's take another look at this board. As I said, it has 4 resistors, 3 of which are connected to the voltage selection jumpers. Basically, when we choose which voltage to set, we simply select which upper resistor to take. The lower resistor has some constant value. Let's see which values the resistors have on this board. This is the lower resistor and it has 249 ohms. This resistor goes to the 3.45 volts jumper and is 432 ohm. This goes to 3.6 volts jumper and is 475 ohms. And last but not least, this 549 ohm resistor is connected to 4 volts jumper. Now let's use the formula from the datasheet and calculate the voltages. Vref is 1.25 volts as I said, and the resistors are as mentioned. Vout is the output voltage and it depends on which of the R1 resistor we select using the jumpers. And as you see, the voltages are nearly like what we measured previously. Always a good feeling when math and the measured values actually correlate. But the point is that the soldered resistors don't fit, and we are not getting the 3.45 volts, 3.6 volts and 4 volts. Obviously some other voltage regulator has been used previously on this board, but that's not a problem, since we can simply choose another resistors. I thought I could just swap the resistors a bit and see if we can get nearly to where we need. For example, if we swap R2 resistor with 432 ohm R1, we will get 3.42 volts, which is nearly 3.45 volts and the voltage which we need for the most 3 volts 486 CPUs. The other 2 resistors are, however, out of range and have to be adjusted accordingly. So I made a table where I use 432 ohm resistors as R2 and calculated R1 for every possible voltage between 3.3 volts and 4 volts in 0.5 volt steps. This is what I got. For 3.45 volts we would need 245 ohms. Here we can use that 249 ohm one, which should be good enough. For 3.6 volts we need 230 ohm resistor, and for the 4 volts about 200 ohms. Unfortunately, I don't have SMD resistors in the size and values as needed, and I also don't want to wait for the order. However, for 3.45 volts setting I just have to swap two resistors which are already there. For 3.6 volts I need 230 ohms one, but I found 220 ohm in the scrap. That would give something around 3.7 volts. That is good enough for now. For 4 volts I have to improvise in a similar way. I don't have 200 ohm resistors, which would fit, but I have those in 100 ohms. So 2 resistors in a row will do the job, even if it looks a bit ugly. Next time I order the parts, I'll take also the required resistors, but for now, to continue, it's fine. So let's test it. And we do have 4 volts. The pair of 100 ohm resistors seem to work. Now there should be 3.6 volts, but since the resistor is a bit too low, there should be 3.7 volts. Yeah, 3.75-ish is also as expected. And the most important voltage, 3.45 volts. Perfect. Now the jumpers can be set to power the CPU through the voltage regulator, which is set to 3.45 volts. For testing, I'll use this Intel 486 DX4100 3 volts CPU. Nice, the CPU gets 3.45 volts, and the postcodes are also running on the analyzer. Perfect. The CPU is also detected properly, and the post screen shows DX4100. Unfortunately, there is still no battery installed, so the board forgets the BIOS settings after every shutdown. I'll come back later to it, but now let's set up the compact flash card once again and try to boot from it. So DOS is booted, and the CPU identification utility reports the CPU properly as well. Let's run the Doom benchmark. Oh, 4597 ticks. That is a very low value for a 100 MHz CPU. Let's see, there is a turbo button header. Let's connect a button. Maybe this board runs in deturbo mode per default. So this is turbo off. Now on. Yeah, it's going faster. Now off again. Okay, so that low value in Doom was due to the deturbo mode. In that mode, such a system runs at about the speed of a DX33. This seems to be more or less right. Let's run Doom once again. (2913 ticks), much better, but still with some space for improvement. Currently this board has no level 2 cache installed, so let's add some. Here I have 8 x 32K 15 nanoseconds fast SRAM ICs, plus one 32K tag. This should bring this board to 256K of level 2 cache in total. That should be sufficient, but there is something unusual about this board. Do you see how the cache sockets are longer than the ICs I'm using? Well, this is due to the fact that this board accepts also 64K and 128K chips, which would bring this board to 1 MB of level 2 cache. An incredible number for a 486, but only really useful when installing a lot of memory. For up to 32 MB of RAM, 256K of level 2 cache should be enough. But with 1 MB of level 2 cache, you could theoretically use up to 128 megabytes of cacheable RAM on this mainboard. Back in the days it was a size which no private person could afford, and no standard software or game did require so much. Okay, the system posts and reports 256K of level 2 cache. Sysinfo now reports 197 points. That should be about right. Anyway, let's try Doom once again. By the way, on the load, the voltage regulator remains barely warm and probably doesn't need any additional cooling. Later, when I test this board for longer, I'll keep an eye on the temperature and maybe we'll glue a small heatsink like this one on top of the regulator. And in Doom we are getting now 2418 real ticks. That's quite a lot faster. But still not what I would expect from a DX4100. I bet with some fine-tuning in the BIOS we can get a couple of percents more out of it. But now let's come back to another annoying thing, the battery. So far this board always forgot the settings after a shutdown. That is very annoying, especially if you want to play with different BIOS settings. So let's help this board to remember. Previously, this board used to have a rechargeable battery, which already started to leak and was removed just in time. Such rechargeable batteries were keeping the clock running even when the system was powered off and were recharged when the system was powered on again. As you see, there is about 60 milliamps charging current which would run into the battery. Now, as alternative for such a rechargeable battery, a cell coin battery CR2032 can be used. On this board there is even a footprint for the battery holder drawn on the PCB. However, it would be dangerous to simply install such a battery here. It is not rechargeable and so, in the worst case, it could explode if forced to charge. I've been talking about this in previous videos already, and there were comments like to use a rechargeable LIR 2032 coin battery instead of CR2032. It has the same size and is actually rechargeable. The problem is that it is a lithium battery which needs additional charging circuit without which the battery could overcharge, overheat and explode. So neither LIR 2032 nor CR 2032 is directly usable here. However, every board can be simply modified for the non-rechargeable CR 2032 battery. Non-rechargeable sounds bad, but it lasts up to 10 years, so it's usually fine. As I previously said, the problem is that when the system is powered on, the battery gets recharged. So what we need to do is to prevent charging current from running into the battery, but also prevent the battery from draining when the system is powered on. So, on this board, the responsible circuit is quite simple. Of course, I don't know every board, and I measured it off camera previously, so here the 5 volts from the power supply are going into this diode D2. Out of the diode it goes into the resistor R13 below, and after the resistor, through a wire in the PCB, the trace goes directly into the plus pole of the battery. So when system is powered on, the current would flow through D2 and R13 into the battery and charge it. Beside the battery, this wire is also connected to the input of another diode, D1. The output of D1 is then connected to the RTC module in the chipset. So, to prevent the battery from charging, we need to remove the resistor R13 and solder it between the output of D2 and the output of D1. This way, the current from the power supply will be redirected to the RTC module and D1 will prevent it from running back to the battery. The battery is connected to the input of D1, but is now disconnected from the PSU and shouldn't be recharged. Let's test. The power is now on and Nearly the same 4.7 volts we should have on the output of D1. That's right. And on the input of D1 we have 0.2 volts. That's okay. That diode has a small amount of reverse current leakage which generates a little voltage. However, if I measure now the charging current on the battery, it should be around 0 amps. Yeah, next to nothing. Now the battery shouldn't be charged anymore, but power the clock when the power is off. Let's install the battery holder. Unfortunately, the one which I have doesn't fit. The PSU connector is in the way. I'll use my soldering iron to cut a little bit of plastic away. Yeah, that doesn't look nice, but will do the job. Let's solder the battery holder. So the battery is new and has 3.3 volts. Here after D1 we have 3 volts, that's good enough. The battery will not be charged and should now hold a couple of years. Back in BIOS, let's do some settings, save it, power off the system and see after a while if the settings are still there. Nice, we are about half an hour later, the clock is still ticking and all the settings are still valid. Now where the settings get saved, let's see if we can do something about the performance. As you remember, with conservative BIOS settings we got 2418 real ticks. That is actually quite slow for a 486DX4100. So let's try to improve the BIOS settings a bit. Yeah, there is not much what we can do. Only DRAM write cycle can be reduced to 0 wait states. Everything else seems already be at fastest settings. Yeah, and at 0 wait states the system seems not even to boot. Let's set the write cycle back to 1 wait state. Well, the system boots and Doom benchmark shows again the same result. That is a bit disappointing. This system should run at least 10% faster, and even then it would still be average. Okay, the original BIOS unfortunately didn't give a lot of options to play with. So I modded the BIOS of camera and unlocked a couple of interesting options to try. If you are interested to know how I did that, I made a video about it a while ago. Feel free to check that out. So I modded the BIOS B2 and called it B2.1, which shows some more options in the chipset features setup. One of the most interesting and misleading options which you want to activate is slow memory refresh. The dynamic memory holds the ones and zeros as a charge, which gets lost after a while, and so every memory cell has to be periodically refreshed to keep that charge. Every time the memory is refreshed, the system has to wait until it's done, and of course this slows down the system significantly. Very old memory modules had to be refreshed quite often, but more modern DRAM could keep the data reliably for longer periods of time. What means that the memory doesn't need to be refreshed quite as often. The option for that is called slow DRAM refresh. That improved the Doom benchmark to 2368 ticks. And although measurable, that is only an improvement by around 1 FPS. I played with some other options which I unlocked and they all brought together around 100 ticks improvement. Still not enough to call it an expected performance. The system was still slower than it should be. But then I looked into PCI configuration setup, which is usually used for resources reservation and such stuff, and discovered there are a couple of other performance entries which I didn't expect to see there: CPU to PCI buffering and burst writes, which I happily activated. That options pushed the system finally into the expected level of performance, and Doom benchmark was finished with 2074 ticks, which I was happy with for a DX4100. That didn't break any records, but is a solid result. However, this board supports also frontside bus of 40 and 50 MHz, so I decided to push the limits a little bit. Intel 486DX4100 has a fixed multiplier of 3, and at 40 MHz frontside bus it came up to 120 MHz. But unfortunately it didn't even boot with that. I tried to increase the voltage up to 3.75 volts, but with no success. So I tried another CPU, which I have, an AMD 486DX4100, which happily booted at 120 MHz and finished Doom benchmark with 1830 ticks. I tried to ramp up the frontside bus to 50 MHz, but that was not possible with that CPU. It has a fixed multiplier of 3, and 150 MHz effective clock was just too much for it, even at 4 volts. However, in my collection I also have an AMD 486DX2100, which has variable multiplier of 2 and 3. Setting that to 2, the system booted fine at 50 MHz frontside bus and 100 MHz effective clock. Doom benchmark finished now with even faster value than at 120 MHz with frontside bus of 40 MHz and delivered 1805 ticks. Unfortunately, this DX2 refused to boot with the multiplier 3 using any frontside bus above 33 MHz, but I guess it's fine and we got some nice results. And I think this video already got quite long, so time to wrap up. Another nice 486 mainboard back to life. It is Soyo SY-030H, a late 486 PCI mainboard. I replaced the broken memory slot, which works fine. The voltage regulator has been restored and works as well, though I will have to add some proper resistors later to get the voltage more to the specs. But the good news is that it doesn't get hot and doesn't need any additional heatsink. The battery is now a CR2032 coin cell, which will not leak and can be easily replaced. I had to make a small change on the board to prevent the battery from charging. Moving a small resistor to another place did the trick. What else? Yeah, I added the 256K of cache, which makes the system faster by about 25 to 30%, and of course not only was the BIOS ROM re-added, but also patched a little bit, and after some experiments the whole system delivered some solid performance. All in all, nothing to break world records with, but still a nice board with wide range of frontside bus clocks, 3V CPU support, PCI and support for up to 1 MB cache, which allows to install massive amount of cacheable memory on this mainboard. A very nice exemplar, and I had my joy to tinker with it. And I hope you enjoyed this video as well. I'm always glad about your feedback below. As always, thank you for watching and goodbye.